It is the 5th of September 2025, approximately 11:32 a.m. Continuing along with the exercises from earlier. Exercise 20. This is a different sort of whiteboard, so let's see what I can make of it. For x, an element in group G, show that x and x inverse have the same order. So what would be the intuition for this? Order n means, well, we've discussed this. X to the n is equal to 1. Inverting both sides preserves equality and turns x to the n into parentheses, open parentheses, x to the negative 1, close parentheses, to the power of n. So the same n works for x to the negative 1. Symmetrically, any power that gets rid of x to the negative 1 also gets rid of x. So, no, wait, sorry. I already did this one. If I'm not mistaken, I've already done this one from, maybe did something similar. Let's see. No, I already did this one. I just forgot to turn the page. On to 21 then. Yeah. Okay, so for 21, that's different. For 21, let G be a finite group. And let x be a member of G, an element of G have order n. Now we're asked to prove, we're told prove that if n is odd, then x is equal to, open parentheses, x squared, close parentheses, k, for some k within the positive integers. Intuitively, if the order of x is equal to n and n is odd, then n is equal to 2k minus 1 for some k. Since x to the n is equal to 1, multiplying by x pushes the exponent up by 1, so x to the 2k minus 1 times x is equal to x to 2k, which is equal to x. But x to the 2k is equal to, open parentheses, x to the, well, x squared, close parentheses, to the power k. So x is equal to, open parentheses, x squared, close parentheses, to the k. So, talking about this more rigorously, assume the order of x is equal to n. Furthermore, that n is odd. Then there is k within the positive integers with n is equal to 2k minus 1. By definition of order, we have that x to the n is equal to 1, which implies that x to the 2k minus 1 is equal to 1. So let's check how that actually looks on the camera. All right, that's fine. It's a little much erasing. Maybe this one's better. Yeah. Okay. So we have that that's equal to 1. Multiply both sides on the right by x. And what we get is x to the 2k minus 1 times x is equal to 1 times x. Using the exponent law, x to the a times x to the b is equal to x to the a plus b. That's from group associativity. X to the open parentheses 2k minus 1 close parentheses plus 1 is equal to x, which implies x to the 2k is equal to x. Now, oh, that's nice. Okay. Now, rewrite the left-hand side as a power of x squared. What we get is that x to the 2k is equal to open parentheses x squared close parentheses to the k. Therefore, x is equal to open parentheses x squared close parentheses to k as required. QED. So not much to that one. Which means it's either something that's fairly conventional or, I mean, all of this is fairly conventional, but I mean, like, in terms of, you know, me studying this, it's like, well, it's either fairly conventional or I'm missing something. So, no, looks fairly straightforward in comparison to some of the other ones we looked at. All right. On to 22. First, check that. It's working fine. So, exercise 22 states if x and g are elements of a group G, prove that the order of x is equal to the order of g minus 1 x g. Deduce that the order of AB is equal to the order BA for all AB in G. Intuitively speaking, conjugating by G is just a change of coordinates in a way. Scare quotes on that. Powers pass cleanly through. So, open parentheses, the inverse of G times X times G itself, close parentheses to the power K, is equal to G, the inverse of G times X to the power of K times G. So, X to the N is equal to 1 if and only if open parentheses G to the negative X times G, close parentheses to the N is equal to 1. Hence, the orders match. Taking X to equal AB and G to equal B gives B inverse times open parentheses AB close inverse times B, which is equal to B times A. So the order of AB is equal to the order of BA. But how would we show that more rigorously? We first prove this the power pushing identity by induction. Yeah, which is literally what it's doing there. So whenever I say power pushing, it's like, you know, you have open parentheses G to the negative 1 times X times G to the K. Well, that equals G to the negative 1 times X to the K times G. Conjugating by G, that is, in the case in which you're conjugating by G. So we first prove the power pushing identity by induction, and what that is more, I guess, explicitly is to say for every K within the positive integers, open parentheses G to the negative 1 times X times G, close parentheses to the power K, G to the negative 1 times X to the K, G, and we set our base case K to equal 1. Yeah, we want to prove this. We set our base case equal to 1. K base K is equal to 1. So what do we do from there? G to the negative 1 X G, open parentheses G to the negative 1 times X times G, close parentheses to the 1 is equal to G to the negative 1 times X times G. Now, the inductive step of this assume that open parentheses G to the negative 1 times X times G times K, close parentheses to the power K, is equal to G to the negative 1 times X to the K times G. That's our inductive hypothesis. Now, we say that then open parentheses G minus G to the negative 1 times X times G, close parentheses to the K plus 1, is equal to open parentheses G to the negative 1 times x times g, close parentheses, time to the power k, times, open parentheses, g to the negative 1 times x times g, close parentheses, which is is equal to g to the negative 1 times x to the k times, open parentheses, g times g to the negative 1, close parentheses, x times g, which is equal to g to the negative 1 times x to the k plus 1 times g. So therein we have our identity, right? Because it holds for k plus 1. K greater than or equal to 1. Alright. And on to the equality of orders. Oh boy, okay, so we had the conjugating, now we have to do a little bit more. Okay, so equality of orders. Okay. So for the equality of orders, suppose the order of x is equal to n, and that is finite. Then x to the n is equal to 1. So, open parentheses g to the negative 1 times x times g, close parentheses to the n is equal to g to the negative 1 times x to the power n times g. That is equal to g to the negative 1 times 1 times g, which is equal to 1. For some n. So, the order of g to the negative 1 times x times g is less than or equal to n, by definition of the order of an element. And so, conversely, if the order of g to the negative 1 times x times g is equal to k is finite, then open parentheses g to the negative 1 times x times g to the close parentheses to the k is equal to 1. So, for some k, yeah, we already defined k as belonging to the positive integers. So, 1 is equal to, open parentheses, g to the negative 1 times x times k, close parentheses, to the power k, which is equal to g to the negative 1 times x to the k times g, which implies x to the k is equal to g times 1 times g to the negative 1, which is equal to 1. So the order of x is less than or equal to k. So therefore, the order of x, so look, this is here, here. So from that, what can we say? Well, therefore, the order of x is equal to the order of g to the negative 1 times x times g in the finite case. Okay. I mean, swap that out for k, right? And then it's finite because we chose k to be an arbitrary positive integer, such is the case with n here. So we can say this for notational purposes. Therefore, the order of x is equal to the order of g to the negative 1 times x times g in the finite case. The same argument holds like it did before whenever we were looking at that other case where we were switching these things around, right? It's like if we apply the x has infinite order a priori sort of thing into this big structure, we'll find that it's also, we find that it leads to a contradiction. So that is what it is. Yeah, so therefore the order of x is equal to g to the negative 1 times x times g in the finite case, and the same argument shows x has infinite order if and only if g to the negative 1 times x times g does. Now we have to work on the deduction step to this whole thing. So, deduction, the order of AB is equal to the order of BA. So let's let x equal AB and g equal B. Then g to the negative 1 times x times g is equal to b to the negative 1 times ab times open parentheses ab close parentheses times b, which is equal to ba. So by conjugacy invariance, by the conjugacy invariance. All right, so this is what we just looked at, right? So g to the negative 1 times x times g is equal to b to the negative 1 times AB times B is equal to BA. So by this situation, by this, well, by the conjugacy invariance, we have the order of AB is equal to the order of BA. Let's move on to exercise 23. Try to check that. Still good. All right. Let's do 23. Suppose that x is an element in G, and the order of x is finite. It's equal to some n which is less than infinity. If n is equal to st for some positive integers s and t, prove that the order of x to the s is equal to t. So, what's the intuition for this? Well, you know, order to the n, as we mentioned earlier, as is the definition, means x to the n is equal to 1, and no small positive power of x is 1. So, well, we have our basic definition of what order is, but for x to the s, the tth power is equal to, open parentheses, x to the s, close parentheses, to the t, which is equal to x to the st, which is equal to x to the n, which is equal to 1. So the order of x to the s divides t. If, open parentheses, x to the s, close parentheses, to the k is equal to 1, then x to the sk is equal to 1, hence n divides sk. Since n is equal to st, this forces t to divide k, so the smallest such k is t. Let's look at that more rigorously. So, assume that the order of x is equal to n with n equal st and st being a positive integer. So for the first step, let's just consider this. Open parentheses, x to the s, close parentheses, to the t is equal to 1. Okay, so open parentheses, x to the s to the t is equal to x to the s is equal to x to the st is equal to x to st. So, which is equal to x to the n, which is equal to 1 by definition of order. So, the order, well, so the order of x to the s is a positive integer dividing t. Right. So we have that in line there. Now let's look at the minimality of t. So we have that, at times it's well, we have that case. We have that. This is the case here. Now let's move on to discussing the minimality of t, showing that it could only ever be equal to t. So, minimality of t. Suppose that we have open parentheses x to the power s, close parentheses to the power k is equal to 1 for some k within the positive integers. Then, open parentheses x to the s, close parentheses to the k is equal to 1 implies x to the sk is equal to 1. By the definition of the order of x is equal to n, this is equivalent to, let's think about this, equivalent to n divides sk. The definition of the order of x is equal to n. This is equivalent to n divides sk. So, what does that mean? More concretely. So, let's using n is equal to st divides sk implies t divides k. Therefore, every positive k with open parentheses x to the s, close parentheses to the k is equal to 1 is a multiple of t. Okay, and if it's a multiple of t, what does that mean? Well, if it's the case that every positive k is a multiple of t. The least such k is t. And we combine these steps, right? We can combine these steps to show that the order of x to the s is equal to t. And so we're done with 23. Let's move on to 24. Assuming everything's okay on this end. Yep. That's cool. I like the minimality argument. It's very nice. So, let's look at exercise 24. If A and B are commuting elements of G, prove that open parentheses a to the a times b close parentheses to the n is equal to a to the n times b to the n for all n within the integers. And we're given this note: do this by induction for positive n first. Intuitively, when AB is equal to BA, powers separate cleanly, right? Each time we append another AB, we can slide the new A past all existing Bs, and the new B past all existing A's. So, open parentheses, AB, close parentheses to the k plus 1 is equal to A to the k plus 1 times B to the k plus 1. Negative exponents follow up from open parentheses AB, close parentheses to the negative 1 is equal to B to the negative 1 times A to the negative 1. And the fact that inverses also commute. So, as the habit goes, to look at this more rigorously, let's use a proof and say, assume throughout that AB is equal to BA. Now, let's follow instructions here. Step 1. Positive exponents via induction. We show open parentheses AB, close parentheses to the power n is equal to A to the n times B to the n for all n within the positive integers. Let's set our base case. Let's set our base case equal to, base n is equal to 1. So with base n equals 1, open parentheses a, b, close parentheses to the 1 is equal to ab, which is equal to a to the 1 times b to the 1. Ooh. So what would the inductive step for this be? Okay, so the inductive step assume that open parentheses ab to the k is equal to a to the k times b to the k for some k greater than or equal to 1. It's our inductive hypothesis then. Open parentheses ab to the k plus 1 is equal to open parentheses ab to the k times open parentheses ab, close parentheses, which is equal to open parentheses a to the k times b to the k, close parentheses, times ab, close parentheses, is equal to a to the k times open parentheses b to the k times a, close parentheses, times b. See how about that? Okay. Now, because AB equals BA here, they're commuting elements, right? So A commutes with B to the K. Because that's just, multiples of that. So B to the K, A is equal to A to the B, A times B to the K. So, open parentheses A, B, close parentheses to the K plus 1 is equal to A to the K times close parentheses, open parentheses, A to the B, A times B to the K, close parentheses, B, which is equal to, I'm going to write it all the way over here, open parentheses, A to the K times A, close parentheses, open parentheses, B to the K times B. Yeah. And this is equal to A to the K plus 1 times B to the K plus 1, which is what we wanted. So, by induction, open parentheses, A, B, close parentheses to the n is equal to A to the n times B to the n for all n greater than or equal to 1. Right, so then we move on to the next step, which is the 0 exponent. These are all the positive ones, and then we'll have to do the negative ones eventually. Let's check that. Good to go. So for step 2, the 0 exponent by convention, x to the 0 is equal to 1. For any x within G, x to 0 is equal to 1 for any x within G. Hence, open parentheses AB, close parentheses to 0 is equal to 1, which is equal to A to the 0 times B to the 0. Now let's look at the negative exponents for step 3, which I think, you know, in every single instance where we're trying to look at like the exponential, what is it? I don't want to call it the exponential case in which we're trying to look at elements, because I feel like that brings up, you know, Euler's number and stuff like that whenever I mention it. But for every case like this, it seems like, you know, the 0, n equals 0 is going to be the easiest step. But let's go to the negative exponents. There's probably a case out there where it's like, no, it's actually the hardest. So it's like, screw you. That's just how it works. So let n equal negative m, with m being within the set of positive integers, within the positive integers. So then open parentheses a, b, close parentheses to the n is equal to open parentheses a, b, close parentheses to the negative n, which is equal to open parentheses a, b, close parentheses to the negative 1, close parentheses to the n. Yeah, so m is oh boy, okay. Let's think about that a bit, because I need to make sure that that's actually kosher. But I don't see how it's not kosher yet. Let's see. So if it's 2, and 2 after 2n. No, that follows. Okay. So we can remember this rule, right? So, So using the inverse of a product rule, we have that open parentheses ab to the negative 1 is equal to b to the negative 1, right? We had that with the uv earlier, but in this case we're using ab, is equal to b to the negative 1 times a to the negative 1. So from the fact that these things commute from, well, let me go back, yes. From AB is equal to BA, it follows that inverse of A and inverse of B also commute. So we may apply, in fact we do apply the positive exponent case whoops, what am I doing? Okay. Positive exponent case to the inverse of B and the inverse of A. what does that get us? Well, that gets us that open parentheses b to the negative 1, the inverse of b times the inverse of a, close parentheses, to the power m is equal to b to the negative m times a to the negative m, which is equal to a to the negative m times b to the negative m. Now, since n is equal to negative m, we have a to the negative m is equal to a to the n, and b to the negative m is equal to b to the n. Remember from define, yeah. So, open parentheses ab, close parentheses to the n is equal to a to the n times b to the n. Now, yeah, so combining the three steps, open parentheses ab, close parentheses to the n is equal to a to the n times b to the n, and this is for all n within the integers. Hopefully didn't miss anything. Don't like missing things. So let's go on to 25. How much time do we have left? Some time left. So 25, exercise 25, prove that if x squared is equal to 1 for all x within G, then G is abelian. Huh. I see. Whoa, that's pretty neat. Okay. So the intuition on this is if every element is an involution, x squared is equal to 1, then x is equal to x is equal to its inverse for all x, right? So apply this to a product AB, open parentheses AB, close parentheses, squared is equal to 1. We have AB is equal to open parentheses AB, close parentheses to the negative 1, but open parentheses AB, close parentheses. So the negative 1 is equal to b to the negative 1 times a to the negative 1. That's that rule, remember. And with a to the negative 1 equal to a and b to the negative 1 equal to b, this collapses to ab is equal to ba, which is what we want. Which is what we want in order to show that it's abelian. So let's do this more rigorously with a proof. So assume x squared is equal to 1 for all x within G. Step 1, every element equals its inverse. That's what we want to look at, that aspect. So let's fix x within G from x squared equal to 1. We have x dot xx is equal to x times x is equal to 1 by definition of the inverse. So by definition, of inverse, this implies x to the negative 1 is equal to x. So let's, so we have here with that step that every element equals its inverse in this case. Now let's look at the case of the inverse of AB. So step 2, compute, we want to compute open parentheses AB close parentheses to the negative 1 explicitly. So for arbitrary A, B within G, open parentheses A, B, close parentheses times open parentheses B to the negative 1 times A to the negative 1, close parentheses is equal to A times open parentheses B times B to the negative 1, close parentheses, times A to the negative 1, which is equal to A times 1 times A to the negative 1, which is equal to A times A to the negative 1, which is equal to 1. Right. Now let's swap these around. See if they're equal to each other. That way. Okay. So let's see about that. B to the, open parentheses, B to the negative 1 times A to the negative 1, close parentheses, times open parentheses, A, B, close parentheses, is equal to B to the negative 1 times open parentheses, A to the negative 1 times A, close parentheses, times B. Now, this is equal to B to the negative 1 times B, which is equal to B to the negative 1 times B, which is equal to 1. So open parentheses A, B, close parentheses to the negative 1. Well, that's just equal to B to the negative 1 times A to the negative 1. Yeah, to show proof of that step. Now, let's see if we can pull off concluding that AB is equal to BA. Check this. That's good. Now, step 3. For step 3, conclude AB is equal to BA. Since x squared is equal to 1, holds for every x, it holds for x is equal to AB, such that we have open parentheses AB squared, AB close parentheses, squared is equal to 1, which implies AB is equal to open parentheses AB close parentheses negative 1. Okay. So as well, AB is equal to It's inverse. Yes. Okay, so using, you can sort of see where this is going, right? So using step 2 and step 1, AB is equal to open parentheses times AB to the negative 1, which is equal to B to the negative 1 times A to the negative 1, which is equal to BA. So we can swap them around. Swap them around via the version. And so as A, B within G were arbitrary, G is abelian. Now, let's move on to exercise 26. So it says here, assume H is a non-empty subset of the group G O under multiplication, which is closed under the binary operation on G and is closed under inverses that is for all HK within H, HK within all HK within G. Wait. It's closed under inverses. So it's closed. So HK. All HK within H. Oh, right. Yeah. H comma K within H, HK within H, and the inverse of H within the group. Well, yeah, it's a group. So then H prove that H is a group under the operation under the multiplicative operation restricted to H. Such a subset H is called a subgroup of G. Of G. There we go. This one is going to be a bit longer than the others. Well, no, it's just wordy. Let's think about it. Alright, so, well, intuitively we already know the law and an associativity from G. We already have that. Non-empty plus closed under inverses gives us a inverse within H, so A times A inverse, which is equal to the identity, is also within H, producing an identity inside H. So the given closure keeps all products in H, thus H inherits every group axiom, right? So it's kind of the definition of the thing, but you know, let's look at this more rigorously. It's here. Proof. Okay. So we use multiplicative notation for juxtaposition for the group law. Yeah, I misspoke earlier whenever I called H a group because that's what we're trying to prove. We don't know that. So for the group law and verify the axioms on H. So let's start with associativity, since that one's, we kind of guessed that that one kind of has, well, it inherits that from G, right? So, I mean, I mentioned that in the intuition part of this, but associativity on H. So, for any X, Y, Z within H, since H is a subset of G, and the operation is the same as in G, we have that open parentheses xy close parentheses times G is equal to x times open parentheses yz close parentheses in G. Hence, also as elements of H. The operation is merely restricted by, you know, what H is because it's contained within G. It's not a proper subset though, so let me think. Restricted to H, okay. Restricted to H, we had mentioned that in the early thing, so the operation is merely restricted. So we have associativity. Now how about the identity element? Belongs to H. We want to show this, right? We want to see that. Because because H is not the empty set, right? So yeah, that's by assumption. So we assume H is not empty. So because of that, we can choose some element A within H. Now, there exists, well, yeah, we choose in this case an element A within H by the inverse closure. So by the inverse closure hypothesis, so it's like, well, we set up those different things that define what H is there at the beginning. So A is within, the inverse of A is within H. So let's look at this a bit more depth-wise, right? So by the product closure hypothesis, which is laid out there, A times its inverse is also contained. Well, is it? Let me think. Yeah, because the inverse is also in H, and so, well, by what we laid out earlier, in this case the product closure hypothesis, we have that A times its inverse is also within H. In G, A times A inverse is equal to the identity of G so I might have to get a bit more specific with that. Say E sub G, hence E is equal to A times A negative, A to the negative 1, A times A inverse, that's equal to the identity as well. For any H within H, since, these are both, yeah, since E is the identity, and it uses the same A's, right? So it's the identity in G using the same A and A inverse as defined. E to the H, E sub H, E times H is equal to H, and H times E is equal to H. So E to the G X as the identity on H as well. So it should be capital E to the H. E sub H. Now, how about the case with inverses? This was already kind of shown there, but let's do something a bit more explicit. This is given such that for every h within h, we have h inverse within h, and in G, we have h times h inverse, h's inverse is equal to the inverse of h times h. So each element of h has an inverse in h. I mean, that's a lot to say. Well, it's like by the hypothesis from earlier, it contains its own inverse, right? So each element contains its own inverse, but what is this? This is putting it as like more of a definitional thing, and with its relation to G further clarified. So that's something. Now, let's look at the closure in H. So this is also given the same way that this one is, right? So for all hk within H, we have, well, no, that's not an implication, that's just something that's assumed, right? So h comma k within H, hk is within H. So we have H satisfies associativity, and that's really inherited, right? So has an identity, E within H is closed under the operation and every element has an inverse in H. Therefore, H with the restricted operation is a group, and furthermore, a subgroup of G. But we weren't asked to prove, really, that it was a subgroup. So much that it is a group under that operation that we mentioned earlier. So we don't necessarily need to say that it's a subgroup, which is why it's in parentheses. Now, how much time do we have left? Do we have time to go over 27? Yes, we do. Okay, let me check that camera. See that that's working. Yep. So for exercise 27, we have proved that if X is an element of the group G, then H is equal to the set containing X to the n such that n is within the integers. Is a subgroup, now we have it, of G. In this case, it's called a cyclic subgroup of G generated by X. Okay. So the intuition with this, start with all integer powers of a single element x, multiplying x to the m by x to the n. Simply adds exponents, right? So, and inverting x to the m simply negates its exponent. So this set is closed under the group law and under inverses, and it already contains the identity x to the 0, x to the 0 is equal to 1. So let's get into this a bit more rigorously with a proof. So let H equal the set containing x to the n such that n is within the integers, x is an integer, and that whole thing is a subset of G. We verify, let's see. Yeah, we verify subgroup conditions. So for example, in the exercise, well, in the previous exercise we looked more closely at that, but let's look at this. So non-empty, is it non-empty and identity present? Is the identity present? Well, since 0 is within the integers, we have that x to 0 is equal to 1, which is contained within H. And we can also say that, okay, this means that H is not empty. Is not empty. Yeah, it's not empty. And 1, the identity element, is within H. Alright, so it's pretty straightforward there. Now let's look at closure under the operation. I was kind of worried about this board for a moment, but it seems to be fine. Closure under the operation. Take arbitrary AB within H, then A is equal to x to the m and B is equal to x to the n for some m n within integers. So using the exponent law we had earlier, AB is equal to x to the m times x to the n, which is equal to x to the m plus n. It's contained within h. Go back to exercise 19. Let's take a look at that. Just to make sure that what's written isn't just taken for granted. So yes, in exercise 19, we proved that this was the case. It was literally the first part of exercise 19, so you can just use that there, the exponent law from so let me get a look, see if that's working all right. Yep, okay. Now, so we do have closure under the operation. That is indeed, this is indeed a thing. It is also within H, and it follows from what we've already done. So we have closure within H. Now let's look at closure under inverses. How I wish. Let's see. Under inverses. So let A be within the set H, with A being equal to x to the m. By exercise 19, we showed that. We showed this was also a part A to the negative 1, which part though is equal to open parentheses x to the m, close parentheses to the negative 1, which is equal to x to the negative 1, which is contained, which is within H. So let's see about that. Yeah, that was literally the second part. Was the second part of exercise 19, so it refers to that. So yeah, you always got to check your memory, unless you got photographic memory. Then even if you already wrote the thing beforehand, I think it helps. Helps with like recall. It's like a little recall test. But so here we have the same sort of inheritance deal going on. Associativity is inherited It's interesting how that works because it doesn't have to do with any sort of like specific set of elements, right? I mean, like it's either works like that or it doesn't. So associativity is inherited from G. The operation is the same, right? So can we say overall with 1, the identity element in H, closure, and inverses established, H is a subgroup of G. And that'll have to be it for now.